Hello, ladies and gentlemen. Welcome to another episode of ECG Essentials with Princo. And this is actually our second introductory session. And I want to say a very big thank you to all of you for your support so far, for your likes, those sharing our videos, our subscribers, those who have dropped comments for us to help us improve. We appreciate all of you so much. And we still want to humbly ask that you sustain this support. You keep sharing the videos with all who benefit from them. You give us your advice, through your comments to help us improve. And whilst you are at that, you drop some likes for us and subscribe to our channel at ECG Essentials. Today we want to talk about the ECG paper. We want to look at some of the information we find on this paper and the relevance thereof. And then following shortly in another video, we'll introduce the waves and the straight lines that we find on this ECG paper. Before we proceed, we want to take a look at a few images and take note of as much as we can as these images roll. So we see that these images just show how a standard ECG paper looks like, and some of the information we find detailed on these papers. So let's all go through together by revisiting these images. And we realize outrightly that this ECG paper is just a roll of graph paper, just like we were using back in high school. And like those graph papers has a vertical axis and a horizontal axis. We see on this paper that there are lights or thinner lines. There are also darker or thicker lines as shown in this image. And these lines running vertically and horizontally, they create small squares and large squares. So the thin lines will create small squares that measure 1 millimeter by 1 millimeter, whereas the thicker or the darker lines creates circumscribed larger squares measuring 5 millimeters by 5 millimeters. We notice that there are 5 small boxes that make up one large square, and so we arrived at 5 millimeters by 5 millimeters just by multiplying the 1 millimeter by the 5. We said it is a graph paper that has a horizontal and a vertical axis, and the horizontal axis of the ECG measures time. It measures time in fractions of a second. Sometimes we use just milliseconds, so time in fractions of a second. The horizontal axis, the time in fractions of a second is such that one small square is equal to 0.04 seconds. So that one large square, which is made up of 5 small squares, is equal to 0.2 seconds. That is just multiplying 0.04 by 5. On the vertical axis, that measures the amplitude or the voltage. One small square that measures 1 millimeter actually equates 0.1 millivolts, whereas one large square that is of course made up of 5 small squares is equal to 0.5 millivolts. I'm sure that at this point some of our audience are wondering how some of these values or measurements were arrived at, and although the simplest answer to this question is that the standard ECG machines are set or calibrated as such. Although that is the simplest explanation, It is also, there are a few pointers that can provide us with some information on how some of these values were generated. So let's look at a few of these pointers. And in doing this, let's take a look at the horizontal axis that measures time. The horizontal axis that measures time in fractions of a second. On this axis, the paper output speed, that is the standard paper output speed that is usually used, is 25 millimeters per second. 25 millimeters per second. This paper output speed just means that the rates at which that ECG produces a tracing. The paper output speed that we have just said is standard is 25 millimeters per second. It just means the rate at which ECG produces a trace. So the simple question here is that if within 1 second the ECG tracing, that's the standard, covers 25 millimeters, then for how many fractions of a second would it take for the ECG to produce a tracing on one small square that measures 1 millimeter? So by simple proportion, all we do is to divide the 1 by 25, and dividing by 1 by 25, we arrive at 0.04 seconds. So it is because of this standard rate of 25 millimeters per second, because of that we have this measurement of one small box on the horizontal axis equating 0.04 seconds in terms of measurement in time. Ladies and gentlemen, this then means that if the ECG were to record at any other speed, besides this 25 millimeters per second that we have just mentioned, then we also expect that the corresponding measurements in terms of the time measurements will also change, so that one small box will no more be equal to 0.04 seconds. And in actual sense, the ECG machine affords us that flexibility, to be able to increase or decrease the paper output speed. So for example, if we were to increase the paper output speed to a rate of 50 millimeters per second, then by simple proportion, we expect that one small box on the horizontal axis that measures 1 millimeter will no more be equal to 0.04 seconds, because we will not be dividing 1 by 25, but one small box will be equal to 0.02 seconds, because we will be dividing 1 by 50. That is by simple proportion. And as a matter of fact, the senior colleagues, may find it necessary to either increase or decrease some of these rates or these settings. Sometimes it helps them to define some wave abnormalities, and sometimes may even help them to appreciate or check for some arrhythmias. Similarly, on the vertical axis that measures the voltage, we are also able to either increase the voltage or decrease the voltage if necessary. Although we have stated that the standard voltage is 10 millimeters to be equal to 1 millivolt. 10 millimeters, that is two large boxes being equal to 1 millivolt. It is possible to increase that voltage or decrease that voltage depending on this on the particular situation. So for example, sometimes we find that the waveforms may be way too large. They may be too large so that even some of the waves may be projecting into each other. In that case, it is possible to operate at a half standard of say 5 millimeters to be equal to 1 millivolt, as opposed to the standard of 10 millimeters being equal to 1 millivolt, so that some of these waveforms can be reduced for better appreciation. In the same vein, it is also possible to increase the voltage. For example, when the waveforms appear too small, we can say use a double standard of 20 millimeters being equal to 1 millivolt instead of the normal standard of 10 being equal to 1 millivolt. And at this point, before we even start considering, sinister courses, serious courses of short waveforms, say short QRS complexes on an ECG tracing, it is important to ensure that the standard of 10 millimeters to 1 millivolt is being used. If not, then the interpretation should be done with that consideration. Ladies and gentlemen, because of the importance of some of these values or measurements that we have discussed, the information is usually captured even on the ECG paper. The information is captured on the ECG paper. And we usually find this information at the left bottom corner of the ECG paper, the left bottom corner of the paper. And as shown in this image, we see the 25 millimeters per second. That represents the standard paper output speed. We find it captured here. And also in this image, we find that the 10 millimeters standard is captured here. Even when not clearly shown, we are still able to identify these calibrations. And we do that by looking at the calibration marker. Some texts also call it calibration signal box. And it is no strange thing, but just this rectangle that is shown here in this image at the far left, preceding these leads, this rectangle that is shown there. And we notice that this rectangle has two large squares on the vertical axis, two large squares, that is 10 millimeters. And of course, we have stated that the standard that is usually used is 10 millimeters, it being equal to 1 millivolt. And on the horizontal axis, we notice that it covers one large square that in essence is 0.2 seconds. And using the standard rates of 25 millimeters per second, one large box will be equal to 0.2 seconds. Having discussed the relevance of all this information, it's important to ensure that the ECG is interpreted at standardized rates or speed and say a standardized voltage. That is a standard of 25 millimeters per second and 10 millimeters being equal to 1 millivolt on the vertical axis. If we are not reading at these standards, then in the interpretation that we are giving to our ECGs, should consider whatever standards or changes that we have made in terms of the settings on the ECG. Let's take it a little further for our audience who are already familiar with the basics, these basics that we are discussing. We realize that it's on the same understanding, that is understanding of the standard paper output speed of 25 millimeters per second, that we are even able to calculate the heart rate or the pulse rate from the ECG paper. And we do this, of course, by dividing either 300 by the number of large boxes between two consecutive QRS complexes, or if you are using the small boxes, then it becomes 1,500 divided by the number of small boxes between two consecutive QRS complexes, of course, provided the rhythm is regular. And what is the rationale? We have stated that on the horizontal axis, the standard paper output rate is 25 millimeters per second. and this means that 5 large boxes are actually covered every second. Why? Because each large box measures 5 millimeters. So if 5 large boxes will be printed on every second, then the question we ask is that how many of these large boxes would have been covered on printed on, over a period of 60 seconds. That is over a period of 1 minute, during which we are checking the pulse rate. So by simple proportion again, all we do is multiply this 60 by the 5, arriving at 300 large boxes. So simply, the answer is that within a period of 60 seconds, we expect that 300 large boxes would have been printed on. Because again, 5 small boxes make up 1 large box, then if we wanted to use the small boxes instead of the large boxes, then we are able to use 1005, that is 300 multiplied by the 5, and we divide the 1500 by the number of small boxes. In doing this, the question we are asking, the simple question that we are asking and actually answering, is that if we were to allow the ECG paper, to print on all these 300 large boxes that we expect to be printed on within 1 minute, that is 60 seconds, how many QRS complexes do we expect to see? Of course, these QRS complexes represents the ventricular depolarization that represents the pulse that we pick. How many of these QRS complexes will show up if we were to print on all these 300 large boxes? And that is simply why we do some of these divisions to help us arrive at the heart rate. For our audience who are not familiar with some of these concepts, please do not be startled at all, don't be moved at all. These concepts are actually being introduced prematurely, and it's just to help us establish the relevance of some of these calibrations and measurements we use for the ECG. But in subsequent sessions, of course, we will discuss some of these concepts better. What is rather important for us to do is to memorize, to try to remember these measurements that we have discussed, because apart from the waveform in terms of the shape or the appearance of the wave, that gives us some information for our diagnosis. Every other information we try to use from the ECG is essentially a question of whether a wave or a complex, is taller or shorter than we expect it to be, or whether, say, a wave or, say, a straight line is longer or narrower than it should be. So it's important for us to have these values, off the top of our heads, so that we'll be able to do some of these required additions and estimations that we rely on to make our diagnosis. Of course, that is in addition to the information that we get from the form or the appearance of the waves. Because we have agreed that these values are very important and we need to memorize them, let's make sure we have actually memorized them before we talk about any other thing. So we look at this familiar picture again that shows our famous graph paper. And here we see that there are small boxes that measure 1 millimeter by 1 millimeter, and there are also larger boxes that measure 5 millimeters by 5 millimeters, simply because 5 of the small squares make up 1 large square. On the image again, we see that on the horizontal axis that measures time, one of the small boxes measures 1 millimeter is equal to 0.04 seconds. And on the vertical axis, one of those small boxes is equal to 0.1 millivolts. Then over here we put it together so that one large box that is made up of 5 small squares is equal to 0.2 seconds, and one large box that is on the horizontal axis and on the vertical axis, one large box is equal to 0.5, and then 2 large boxes will be equal to 1 millivolt. Thank you so much again for your audience. We have just tried to discuss the ECG paper, some of the information we find on this paper, and how we should be able to interpret the ECG in the context and in consideration of some of these calibrations or measurements on the ECG paper. Our next video, we will look at the ECG waves and some of the straight lines that we find on the ECG paper as well. The focus on this next video is just a brief introduction of the waves and the straight lines, but we will also have another session to discuss the very details of these individual waves. I can't wait to come your way again with our next episode. But before I leave you, I still want to humbly ask that you sustain your support. You kindly share our videos, drop some likes for us, and give us feedback to help us improve. And whilst you are at that, please subscribe to our channel at ECG Essentials. Thank you so much again, and see you soon. Bye.